Endothermic or exothermic? Exothermic. It's been a while. So that means decomposition reactions, which are the reverse of synthesis reactions, would be endothermic. When you combine an acid and a base in a container, it feels a little bit warm. That's a neutralization reaction. Exothermic. Combustion reactions are? Combustion reactions release a lot of heat. Exothermic. Okay. Good job. Okay, there are a lot of different fuels that provide us with energy. Things like natural gas, wood, coal, gasoline. And most of that energy is going to be stored. Stored energy is potential energy. And what we're looking at is chemical potential energy, because we typically convert that into heat. And the amount of potential energy that's available to be released as heat is related to a couple of different things. What is the substance made of? And then what is the position of the subatomic particles within it? When we are converting chemical energy into heat, we tend to use the symbol delta H, which is a triangle in front of an H. Okay, the delta or the triangle means a change. So this is symbolizing a change in energy that's available as heat. Delta H is also known as the enthalpy change. So enthalpy is a capital H. Okay, so this is the potential energy that could be released or absorbed as heat during a process. Now, the processes that we are looking at could be physical or chemical. It doesn't matter which one. All physical and chemical processes have some sort of an enthalpy change associated with them. And let me give you an example. If we're looking at a combustion reaction, like this one here, with C3H8, it combusts with oxygen gas to produce carbon dioxide and water. The delta H value that's associated with it is written after the equation. It's negative 2221 kilojoules per mole. When you have a negative delta H value, that means it's an exothermic process. Okay? Exothermic processes release a lot of heat energy. And if we had a positive delta H value, what would that be? Endothermic? Yeah, it would be endothermic. Okay, now, what causes the difference in these enthalpy values? Well, it's going to be the chemical bonds. And let's take a look at the energy of chemical bonds. If you take a look at the bottom of the page, the chemical potential energy that's related to like the electron's position to the nucleus is known as bond energy. So chemical potential energy is called bond energy. And if you take a look at the next page, let's talk about what happens when you break or form bonds. If I was going to karate chop a piece of wood, wouldn't that take a lot of energy on my part? Okay. Similarly, if you're going to break bonds, it's going to take some energy to put in to get that to happen. So that means the opposite, which is forming bonds, is actually going to release a bunch of energy. Okay. Now the balance between the two is going to determine whether you have an endothermic or an exothermic process. So if the energy absorbed to break bonds is greater than the energy released when you're forming bonds, you're going to have an endothermic reaction. Okay? And endothermic reactions, as we said before, have positive delta H values. On the other hand, if more energy is released when bonds form than is absorbed when bonds break, you will have an exothermic reaction, and exothermic reactions have negative delta H values. Okay. Now, there are two ways to express the delta H value for a chemical reaction. The first one you saw on the previous page. So the first one was delta H notation. Okay, so delta H notation has that energy change written after the equation, and it's following a delta H symbol. The other one is called, I'm going to put this in a different color, a thermochemical equation. A thermochemical equation has your balanced equation with the value actually in it. So that energy change is a part of the chemical equation. So if we take a look at the chemical equation on the previous page, it was C3H7. Agreed?
H8.
H8, thank you for correcting me. And it was combining with how many oxygen?
2.
How many carbon dioxides were produced?
2.
And how many water?
1. It was 3 carbon dioxides and 4 waters. Oh, I was looking at 2.
There we go. Okay, I'm sorry. Was this correct?
It's 5.
It's 5. How many carbon dioxides?
3. And 4 waters.
So it looks like this?
Yes.
Okay, perfect. All right, so if we're going to write this as, and my underlining is a little bit off. Let's see if I can fix that. Let's move this over. Better? Almost. Okay. So if I'm writing a thermochemical equation, since this was an exothermic process, my delta H value was negative 2221. Agreed? So since it's exothermic, you would put that value on the product side, but you don't have to include the negative. Okay, it's already implied that it's exothermic when you write the delta H value in the equation on the product side. Does that make sense? So if this was an endothermic process, where would I have put that value? On the reactant side. Okay, all right. Now, let's take a look at the next page. On the next page, let's talk about the activated complex, which is this complex that exists for less than a nanosecond when you're converting reactants into products. So when the reactants collide, and they collide in a favorable manner, meaning like the geometry is proper and they have enough kinetic energy to equal the activation energy, they're going to form a high energy, really unstable transition configuration called the activated complex. Okay? So if you take a look at this reaction here, I'm going to use it to explain the activated complex. I've got hydrogen and oxygen gases as my reactants. So here are my reactants here. I'm going to put an R for my reactants. I need to break the bonds between the hydrogen and the iodine. And then I need to form bonds between the HI molecules. These are my products. And this happens within the activated complex. So what's happening is, and I'm going to do this in a different color, my activated complex is right here. So what's happening is the bonds in your reactants are breaking and the bonds in the products are forming. And this is happening in less than a nanosecond between those two processes, okay? And this unstable complex is going to decompose and form your products, which have less energy, which are just a lot more stable. And we can see this in a potential energy diagram. So let's come down here. So the energy changes that take place during a chemical reaction are typically drawn for you on a potential energy diagram. And there are many parts that I would expect you to know. So let's go over the parts. Let me bring this up a little bit. I'm going to outline everything in different colors for you, so you can see what you're going to be responsible for. So we're going to start with red. You should know that the x-axis is the path that the reaction follows. I'm totally fine if you want to abbreviate this as the reaction pathway. just make sure you don't write that this is time. Okay? And then the y-axis is your potential energy. You may abbreviate this with a capital P, capital E for potential energy. Your units are typically given on the y-axis. It says it's in kilojoules per mole. Okay? Now, the curve that we have here in this potential energy diagram is a curve that represents an exothermic process. Okay, so I'm going to make a note that this is exothermic. Okay, and then we need to label the different parts. So we're going to start with the reactants. So typically your reactants are written right here on this horizontal portion of the line where it begins. Now, if we use the reaction that we had before, we had hydrogen combining with iodine to make 2HI. You can write the chemical formulas for the reactants on this line. So those would be H2 plus I2. Okay? And then over here, we're going to write the products. So the products would go over here, and I have 2HI as my products. We good so far with that? Okay. Now, the peak on the curve is your activated complex, and you will sometimes see them put a star there. Okay, so my activated complex is right here. And then my activation energy is going to be wherever the reactants began, which was right here, okay, to the highest point on that curve. So this is my activation energy. And then the delta H value, which is also known as the heat of reaction, is going to be between where the reactants began and where the products are ending, which is down here, where this dashed brown line is. So this is my delta H value, or the heat of reaction, okay? The way that you calculate the heat of reaction, it will always be the same. You're going to take the potential energy of the products minus the potential energy of the reactants. Okay. I'm going to give you some values on the y-axis, and it's not going to be drawn to scale, but I'm going to give you some values so that I can show you how to determine some things, okay? So let's go ahead and I'll use orange. So let's say that right here at the potential energy of my products, let's say this is 10. Here where the potential energy of the reactants are, let's say this is 50. And then up here at the potential energy of the activated complex, let's say this is, I don't know, do you want to say it's like 90? Okay, so there are many questions I could ask you. Some of them could be, what's the potential energy of the products? You would say 10 kilojoules per mole. Potential energy of the reactants, 50 kilojoules per mole. Potential energy of the activated complex, you would just follow this dashed line over to the y-axis, and it's 90 kilojoules per mole, okay? Potential energy of the activation energy is the peak, which is 90, minus wherever the reactants began, which is 50. So this would be 90 minus 50, which is 40 kilojoules per mole. Okay. If I asked you to calculate the heat of reaction, which is the delta H value here, it's the potential energy of the products, which is 10, minus the potential energy of the reactants, which is 50. What would that be? Negative 40 kilojoules per mole. And it makes sense that it's negative because this is an exothermic process. Does this make sense? Okay. Now, some of these reactions that we're going to be looking at are reversible, which means the potential energy curve is reversible. Okay, so if you're looking at this curve from left to right, which you learned how to do, this would be considered the forward reaction. Okay? If you're looking at it in reverse, you'd be reading it from right to left. So this direction would be the reverse reaction. And when it's the reverse reaction, then you're going to make the products over here. These will now be the reactants. And then the reactants over here, these will now be the products. Does that make sense? Okay. So what I want to do is I want to take a look at some practice problems. Let's go to the next page and let's take a look at this sample problem on reading an energy profile. So it says, read the following potential energy diagram and answer the questions. Okay, so you tell me, does this reaction look endothermic or exothermic? Yeah, it's endo. The curve for the exothermic curve on the previous page went like this. The potential energy of the products was less than the potential energy of the reactants. So this was exo, and over here, the potential energy of the products is greater than the potential energy of the reactant, so that's why it's endo. Now, what is the activation energy for my reaction? How would I calculate it?
Subtract heat.
Subtract what? Yeah, the peak.
Minus the 20.
Minus wherever the reactants are. So if my reactants are here, and this is the peak, this would be my activation energy. So this is going to be 100 minus 20. So this is 80, and then your units are on the y-axis. It's kilojoules per mole. Okay. What's the potential energy of the activated complex? So your activated complex is at the peak. So just follow that peak over to the y-axis.
100.
Yeah, 100. Okay. Now they want the delta H value.
Product minus reactant.
Yep, products minus reactants. So your products are here. So this is your delta H. So your products are ending over at 40. So this is going to be 40 minus 20, which is, yeah, it's a positive 20. Now, doesn't it make sense that this is a positive value? Because this is an endothermic process. Okay. All right, let's do another practice problem on the next page. So let's come over here. This is a reversible reaction. Okay. Which reaction, forward or reverse, is exothermic? Good job. Forward. Yeah. Because the product potential energy is less than the reactant potential energy. Okay. We want to calculate the delta H value for the forward and reverse reaction. Let's do the forward first. So here's my reactants. Here's my products. So this is my delta H. And I'm going to put a little F to represent forward. So what would I do to calculate that? What numbers? 10 minus 20. So 10 minus 20 is, yeah, so this is a negative 10 kilojoules per mole. Okay, let's use a different color. So that was my forward. Let's use a different color for the reverse. So in the reverse, we're actually looking between the same, REV. So it's going to be product minus reactant. So what values would I use here?
20 minus 10.
Yeah, 20 minus 10. So this would be a positive 10 kilojoules per mole for the reverse reaction. Okay. Okay, now let's look at the activation energy for the forward reaction. What would that be?
50 minus 20.
Yeah, that would be between here and here. So I'm going to put a little F. So this is 50 minus 20, which is
30.
Yeah, it's 30 kilojoules per mole. You don't have to include that positive there. Okay. All right. Now let's look at the let's do this in red, the reverse reaction. 50 minus 10. So yeah, the peak down to here. So these would be the reactants for your reverse reaction. So this would be 50 minus 10. So this is going to be a 40 kilojoules per mole. Okay. Now, they want the potential energy of the activated complex. That's up here. So what is that value? Yep, 50 kilojoules per mole. Does that value change whether we're looking at the forward or the reverse reaction?
No.
No, it stays the same. Okay. All right, on the next page are some practice problems. I want you to do numbers 1 and 2 with the person sitting next to you, and let's see what you come up with.
This is what Is it because this value is lower than this one? Is the product? I mean, indicate on down. That's 140, not 40. 140 minus 110 alpha. That's the delta change, the triangle. Oh, so it would be 130 minus. No, it would be 140 minus 110. No, 130 minus 110. That's the change. Here, activation. Wait, this is the delta. No, it's between the product and the reactant. So it's product minus reactant. Product is 130, reactant is 110. So that's the P. It's the product. Potential energy of the product is 130. Aren't these the potential energy of the active? Oh wait,
Can we do number 1 before you work on number 2? Is that okay? Are you done with 1? Is the forward reaction exo or endo?
Endo.
Good job. What is the activation energy?
140 kJ per mole.
How much?
140.
40. Tell me what numbers you subtract.
140 minus 110.
140 minus 110, because the activation energy is between wherever the reactants began and the highest point on that curve. Okay, so this is going to be 140 minus 110, which is 30. Okay, good job. Now, what's the enthalpy change?
20 kJ per mole.
20, yeah. So wherever the products are, wherever the reactants began, this is going to be your enthalpy change. So this is going to be 130 minus 110, which is 20. What's the potential energy of the products?
130.
Yeah, your products are here on this line. So you just follow this over the y-axis, you're going to get 130. What's the potential energy of the activated complex?
140.
Yeah, it's up here. You follow that over to the y-axis, you get 140. Okay, go ahead and do number 2.
Well, this is the product, and what's this one called? Yeah. So this activation. Activation goes on the top, but what's the bottom? Yeah. Yeah, that's the activation energy. It's the reactant because it's the and then two is The potential energy of reaction. What is this called right here? Oh, wait, no. Potential reaction. Three yes. Because the 3 is activation. Number 4 would number 4. 4 the delta, yeah. Change because this one's called activation and this one's product. Is number 3 potential energy? So what's this? Wait. This is product. That's reactance. You said last time this is product. Like, you know how this is the reaction right here. This is always product unless it's reversed. It's telling you to do like reverse the product is reactant. But this one is fun.
We're ready?
Okay.
Do you need some help on one of them?
Yeah.
Maybe? Number 3.
Potential energy.
Of
The activation.
if it was all the way down here.
Oh, okay.
Let's okay, maybe you'll see it if we go through each one. Okay, if I'm looking at this Roman numeral 1, what are you saying that is?
Activation energy.
Of what? Forward or reverse reaction?
Forward.
Yeah. It helps if you specify. Okay, and then I think you'll see it. If we're looking at Roman numeral 2 right here, what would that be?
Activation energy for reaction.
Potential energy for?
Reactant.
Okay, so this would be the potential energy of the reactants for which reaction? Yep. What else could you say?
Potential energy of the product.
Uh-huh. Or potential energy of the product for the reverse reaction. Okay. Does that make sense? Okay. This Roman numeral 3 would be what?
Activation energy for reverse.
Yeah. Activation energy of the reverse reaction. Okay. And then this Roman numeral 4 would be what?
Enthalpy change.
Enthalpy change. Yeah, or it's also known as delta H, or the heat of reaction is typically what they call it when we're looking at potential energy diagrams, okay? We good with that part? Okay. Next page. Last page. Let's talk about catalysts. So adding a catalyst allows us to take a different pathway, which is known as a reaction mechanism. It's kind of like taking a different street or a different road that's faster and better to get us to produce product, okay? So catalysts provide an additional reaction mechanism with a lower activation energy. The results are we get a faster reaction rate. And remember, catalysts don't get consumed, and they also don't get changed during a chemical reaction. So how does this look on a potential energy diagram? Well, if you take a look at the potential energy diagram down here, a lot of potential energy diagrams in like intro textbooks will show you a catalyzed reaction line, it's going to be usually a dashed line or it's drawn in red, and you're going to see it underneath the original line. Okay, so this would be your catalyzed reaction. And in a catalyzed reaction, we typically have more than one activated complex. So that's why you see multiple peaks in the catalyzed reaction. Okay, and if we were to calculate the activation energy for the catalyzed reaction, you'd still follow the same format. You would look at where the reactants began, and then you would go to the highest peak on that catalyzed reaction, and that would be your activation energy. Does that make sense? Mm-hmm. Okay. And that's it for this section.